Let me introduce our first speaker, Wendy Waudby from Cascade Energy. Wendy has 15 years of experience in energy efficiency, wastewater treatment plant design, reuse, and wastewater service charges. She has worked as a consultant and a regulator and worked for a wastewater agency. Wendy graduated from Cal Poly San Luis Obispo with a bachelor and a master degree in civil and environmental engineering. So now I'll turn it over to Wendy. Hello, Wendy.
Sorry. It just took me a second to figure out where the unmute went. Sorry. Thank you, Meow Meow.
Yeah, we can.
Great. So Cascade Energy provides services for energy efficiency, organizational and technical coaching, low and no cost opportunity identification, ongoing energy monitoring and tracking, opportunity implementation assistance, capital project evaluation, as well as energy management program development. Why should we care about conservation? Well, water, sourcing, treatment, distribution, collection, and wastewater conveyance, treatment, and disposal accounts for about 3% of our nation's energy consumption. We've got power providers where their capacity is becoming constrained, and conservation is typically the lowest cost resource. And then power companies also want to be able to attract new customers and allow for growth. So nationally, the energy used by municipal water and wastewater treatment plants typically accounts for 35% of a municipality's energy budget. So it's a significant cost. And wastewater treatment plants generally they're large energy consumers with pumps and motors and equipment that's running all the time. So just to give you a sense of scale, if you've got a 10 horsepower motor that's running all year, all the time, it's going to use 65,000 kilowatt hours in a year. If it's a 2 horsepower motor, it's going to use 13,000 kilowatt hours a year. If you've got a 5 kilowatt space heater and that's running 10 hours a day, 5 days a week, it's going to use about 11,000 kilowatt hours, which is very similar to that 2 horsepower pump. A 60 watt light bulb is going to use 526 kilowatt hours a year. So why should you care? Well, regionally, electric rates are heading up, and the electrical costs associated with pumping and treatments often the highest non-labor cost for municipality. And it's one of the few costs that can actually be reduced without impacting water quality. So pumps, if we just look at pumps, the operation and maintenance cost over the lifetime is actually 70 to 80%. So only 20 to 30% of that cost is capital. And now premium efficient motors are the minimum standard for new equipment in the US. But for some cases, there's also super premium motors that have even higher efficiency. And if you choose to use those, there could be an incentive for that. And the lifetime cost of most equipment is incredibly dependent on its efficiency. So efficiency is really important to consider. So typically systems are designed for 20 years predicted flows and then built with low bid project delivery methods. So the chances are you're running at less than your best efficient point on most of your equipment. And so sometimes that means your equipment's working harder than it needs to. And now SRF grants and loans have green requirements, so energy projects can qualify. What's in it for you is a significant incentive rate. So depending on your utility, it can be anywhere from 15 to 25 cents per kilowatt hour saved based on your first year's energy consumption and savings. So if you have an aeration system and you can go from 25 horsepower down to 15 horsepower, you could be looking at $12,000 to $16,000. And there's normally a lot of free assistance in identifying potential projects, shepherding the projects through the system, and performing measurement and verification on what you installed. And then you're going to get that ongoing energy savings for the life of your equipment. And sometimes you get reduced maintenance costs because you're turning off equipment or turning it down. And then sometimes there's aesthetic and comfort improvements. So better lighting might be more safe, better HVAC, more comfortable. You may be thinking, who do I call? Well, so this is a view of utilities in the Bonneville Power Administration service territory. So Bonneville Power Administration is a federal power marketing agency. They're under the Department of Energy, and they've been around since 1937. So their service area covers Idaho, Oregon, Washington, Western Montana, and then portions of California, Nevada, Utah, and Wyoming. And BPA has Energy Smart Industrial Program, which helps their customers and their industrial end users achieve cost-effective energy savings. They have technical expertise and a lot of resources. And then if you're in the there's Energy Trust of Oregon, which is based in the Portland area, and they help customers in Oregon. Energy Trust has Energy Trust, BPA, Idaho Power, Rocky Mountain Power. They all, Avista, any of those providers has very similar programs and incentives. So I'm going to kind of focus on explaining BPA and then give a little bit of information about the other providers, but they do have similar programs. So Energy Trust of Oregon serves customers of Portland General Electric, Pacific Power, Northwest Natural, and Cascade Natural Gas. And then here's just a view of Washington and BPA Energy Smart Industrial Program enrolled public utilities. And then here's a list of ESI utilities within Idaho. So there's a lot of BPA ESI utilities out there. So you might be served by one of them or one of the other power providers. But Energy Smart Industrial Program components, they have an Energy Smart Industrial Partner. That's the face of the program. And then what we're really here to talk about today is the custom projects. And so that's your traditional capital projects. So we're looking for incentives for pumps, fans, compressed air, motors, variable frequency drives, control upgrades, and process upgrades. And as I mentioned, the incentives typically vary from 15 cents to 25 cents per kilowatt hour. And then there's also a cap at 50, depending on who you're served by, 50 to 70% of the project cost. So you're going to get the lesser of either the rate-based incentive or the 50 to 70% of the project cost. And the project cost can include design fees, and it can be the incremental cost between baseline and the efficient equipment for new construction. So let's say you're putting in new aeration basins. It's not going to be the cost of the concrete and every cost associated with all the new basins. If you're putting in turbo blowers, but you could have put in centrifugal blowers that were much less efficient and you're using DO control, the cost difference is going to be the turbo blower cost minus the centrifugal blower cost. And then it's paid based on the M&V savings, and so you do have to pay up front. So the payment's going to come after your project's complete and the savings have been verified. So you still need your capital funds up front. So just to estimate payback, because the utilities are also going to look at payback when they're going to do the incentives. If it's got a 50-year payback, that's not going to be considered cost effective from the power provider's perspective. So let's say you're going to have savings of 100,000 kilowatt hours, and for your provider, let's say you're charged 5 cents a kilowatt hour. So that savings, you're going to save $5,000 a year from that project. And so let's say your project costs $50,000. Well, then that's a 10-year payback, 50,000 divided by 5,000. So let's say that you're in Idaho Power's area and you're going to get 70% of project cost or 18 cents per kilowatt hour, whichever's less. So at 70%, that would be $35,000 incentive, but you're only saving 100,000 kilowatt hours, which is $18,000. So you're going to get an $18,000 incentive. So your cost is going to be 50,000 minus 18,000 divided by the $5,000 a year. So you're going to go from a 10-year payback without your incentive down to a 6.4 payback with the incentive you're going to get. Another program component is small industrial, and it's kind of trade ally driven. And so small industrial is small industrial projects. It doesn't mean that your facility is small. It just means the particular project you're doing is smaller. So an example would be a small 75 horsepower or less compressed air system. So this uses simplified analysis tools, and there's a rapid review and approval process, uses vendors to try to help bring in projects. And the incentive rate is the same as the custom projects incentive. There's not really M&V, just kind of making sure that the controls are tuned to what they were for the calculations and that the equipment was installed. And so ESI has a small industrial. Other programs have similar components that are just called something different, maybe streamlined industrial. So there's things are called different things depending on who provides your power, but you're going to find similar programs. I just wanted to mention the Green Motors initiative that the utilities participate in. So basically, if you take your motor to be rewound, it's gonna, if they do the green motors, then it's gonna retain the original nominal efficiency value. And then the incentive's $1 per horsepower, and that's gonna be credited on your invoice. There's greenmotors.org has the shops, and you can save up to 40% or more of the cost of buying a new motor, and then you know that you're getting that same efficiency that it originally had. So the ESI program has technical service proposal consultants, and they're a pool of BPA pre-approved technical consultants that can help you with scoping assessments, project assessments, M&V and completion reports, track and tune projects, and custom consulting, and their levels of service are level 1 would be time and materials up to 2,500, level 2 would be up to 5,000, and level 3 would be a custom based on a approved proposal. And so to compare that to Idaho Power, they have scoping audits that they have pre-approved companies that can do that. Cascade Energy is one of those. That's free to the customers up to a $3,500 value. That would help you identify a project if you don't really have anything in mind, or if you do have something in mind and just need help kind of coming up with your energy savings. They also, Idaho Power will do a cost share for detailed audit. So for a detailed audit that kind of is a deeper dive and really digs into a project and comes up with all the estimated energy savings for different equipment that's going in, that would be Idaho Power. You as a customer would pay for that, and then Idaho Power would reimburse you up to 75% of the cost of the study, up to $12,500. And their incentive is 18 cents per kilowatt hour, up to 70% of the project cost. Energy Trust of Oregon, they do scoping studies for free to their customers. And those are conducted by program delivery contractors. So your facility has a program delivery contractor if you're an Energy Trust of Oregon customer, or not customer, if you're served by them for your energy efficiency. And then they also do technical energy studies for free. And their incentive is 25 cents per kilowatt hour, up to 50% of project cost. And then Rocky Mountain Power is 15 cents per kilowatt hour, up to 70% of project costs. So kind of looking at retrofit opportunities, sometimes they can be a challenge because of that design for 20 years of growth, kind of the difference between capital costs and O&M costs. And then sometimes there can be regulatory challenges because you really need to meet your permit, and there can be little to no tolerance for errors if you're experimenting. Energy costs are typically considered fixed with a slight adjustment each year for inflation. And we have relatively low power costs, some of the lowest costs in the nation. And really the goal is to produce clean water that's meeting permit. So here's an example in the Pacific Northwest. This was an aeration upgrade. So this facility has an oxidation ditch, and they were running two 40 horsepower brush rotors in one ditch and four 30 horsepower brush rotors in the other. And they took those out and replaced those with fine bubble aeration with DO control and two 50 horsepower turbo blowers. And the turbo blowers are high efficiency and quiet. So their savings for this project was about 400,000 kilowatt hours per year. They were using 50% less energy than the original operation, 50% savings. And then the rate they were paying was 7 cents per kilowatt hour. And so they are saving $12,500 a year in energy on their electric bill. And then their incentive was about $88,000 for the project. So when we talk about designing for 20 years from now, or also the day after tomorrow, that's kind of a key takeaway. An efficient machine's energy consumption should drop as fast as or faster than the load, but great equipment is not going to be efficient at any operating point. It's going to be efficient across a fairly narrow range of loads. So an efficient system needs to encompass enough individual parallel machines to cover the entire range of loads expected over the course of its lifetime. We tend to be really good at picking out equipment that's going to be efficient at the peak load of the future, but we can ignore or downplay what happens the day after startup. So hopefully we'll think about turn down and efficient equipment at all operating points if possible. So in this example, they installed 375 horsepower turbo blowers, and the goal DO was 2 milligrams per liter, but with 2 blowers off and 1 turned as far down as it could go, they were still averaging 8. So the solution for this is they pulled out a 75 horsepower blower and put a 30 horsepower blower in so that they could get the airflow that they needed to meet the DO they were looking for. And this is a common inefficiency we see in new infrastructure. And it's due partly to the requirement to design for future flow and loads, as well as the stacking up of safety factors and worst case scenarios, like the hottest day of the year, foul diffusers, worn blowers, a maximum month load. So there's a lot of reasons it happens, but if it's a new facility and there's room, it's a great time to try to put in equipment that can turn down even farther. So let's assume there's a peak demand for a different system of 800 gallons per minute in the future. So the lowest cost alternative while ensuring redundancy would be to install 2 800 gallon per minute pumps. But we recognize that you're not going to get 8-to-1 turn down. So often the next and selected choice is 3 400 gallon per minute pumps. But if we looked at that 800 gallon per minute peak, it might only be needed 1/1000th of the life of the equipment. So an alternative would be to put in 5 200 gallon per minute pumps. And this is where the incentive program can come in to try to help cover the cost of installing additional equipment that's going to allow the system to operate more efficiently. Another option would be to install the 4 300 gallon per minute pumps and 1 100 gallon per minute pump. So this is a system that installed the 3 middle pumps have 125 horsepower motors, and then the 2 pumps on either end are 40 horsepower. And so for this project, well, for this system, they're part of the time they run the 40 horsepower as the lead, and then when they have higher demand, they're running one of the 125 horsepowers as the lead. And so for this incentive, it was they could have put in the pumps and throttled them, or they installed VFDs. And so the estimated savings was 270,000 kilowatt hours a year, which is just over $13,000 a year in energy savings. And the incentive would be capped on savings, and it could be about $48,000. So it's about 10.7 year payback before incentive and a 7-year payback with the incentive. So how do we match flow to load? Well, we could pick a new pump, we could trim an impeller, We could find additional uses for the water we're pumping. We could recycle flow, or the most common approach is to burn off head by throttling. And the reason that it just uses more energy. So if we look at our design point and we're looking for 900 gallons per minute, then we're going to be operating about 85% efficiency and 575 feet ahead. But then if we only want 700 gallons per minute and we throttle that, it's going to increase our head by about 100 up to 676 feet, and it's going to decrease our efficiency down to 80%. So instead, if we used a VFD, we'd still have our initial operating point, and then if we wanted 700 gallons per minute, we would reduce the speed down to 91%, and the head actually drops by about 30 feet, and the efficiency does drop as well. It goes from about 85% down to 83%, but we're going to get a little more gallons per kilowatt hour, so it's actually more efficient. The VFD is limited and it's turned down even in this case. I mean, at 75% speed, it would be way over on the left of the curve. So a VFD can't solve everything and doesn't necessarily turn down all the way. That's why it's better to put in additional, like a jockey pump if you can, and you have those really low flows. But in this case, wanting 700 gallons per minute instead of 900 to go from throttling to a reduced speed, that would save about 20% to put on a VFD instead of throttling. Another example, for this baseline scenario, there's 2 biotowers, and the baseline case is to use constant speed pumps and let the recycle ratio fluctuate with influent flow. So during the initial years, the recycle ratio would be higher, and then over the years, the recycle flow would be reduced toward the minimum design. So in this case, it would be operating at 5,200 gallons per minute and 34 feet ahead. And then for energy, we use the brake horsepower equation. We get 120 brake horsepower and then 825,000 kilowatt hours per year. So if we're looking at VFDs instead, with the VFD and more sophisticated system, the flow rate can be adjusted down to achieve our desired design recycle ratio. And so in this case, we're only going to have 3,770 gallons per minute per tower. Our head is going to be lower because of lower flow, so lower head loss. And then assuming the pump efficiency and motor efficiency were the same, it goes from 120 brake horsepower down to 72, and from 825,000 kilowatt hours per year down to 511. Oh, and don't forget that the VFD also, you lose 3% efficiency. So this is just another point that if you have a pump that's designed at your best efficiency point and you are just going to constantly operate at that best point, you don't want a VFD on that because it's going to use more energy than if you didn't have a VFD. So that's just one. VFDs are normally great options to save energy, but there are cases where a VFD is not going to save you energy. But in this case, they would save $15,700 a year and an incentive of up to $57,500 to help with the VFD system. This is an example of, they've got a lagoon and they have surface aerators and they don't need as much aeration, but they need more mixing. And so they were running 6 surface aerators. They had more installed, but they still wanted to get more mixing. And so they're replacing their excess aeration with more effective circulation. So they're installing solar bees, and they're connected to power on the shore, because you're not going to get, just based on weather, you're going to want to have them connected to grid power as well. So here's a picture of the installed circulator. So they installed 7 of them, and these actually use less than 1/10 horsepower each. So even with 7, it added up to less than 1 horsepower. And they were able to eliminate 253 horsepower of aeration. So their savings was 1.8 million kilowatt hours per year. They saw no degradation in effluent quality and no discernible increase in odors. So the total cost of the project was $375,000. They got an incentive of about $262,000. And their simple payback without the incentive was 5.2 years, but with the incentive, it brought that payback down to 1.6 years. Some guidelines for finding conservation opportunities. Look for loads that run continuously or nearly continuously. Look at your electrical diagram. You can pick out the big motors to focus on those. Look at equipment that's more than 10 years old. If you have systems that are run on simple or no control, those are great potential opportunities, especially if you have an aeration system with simple DO control. There's probably a lot of opportunity there. So consider VFDs instead of control valves. Consider VFDs instead of dampeners on your odor control. Look at installing additional smaller pumps and using efficient equipment. So you could swap out your motors, use the green motor programs if you're rewinding, check that your pump impellers are correct for your actual conditions, and use your most efficient equipment first and most often. Some aeration system ideas. Usually going from coarse to fine bubble saves 30% energy. Active DO control saves energy. Blowers with good turndown capability. Using a least open valve cascaded control strategy. If you're nitrifying, do you need to? Could you denitrify and get the oxygen back? Could you improve your primary clarifier performance and reduce your BOD load to your secondary? You can investigate alternative aeration options, and new surface aerators are more efficient at transferring oxygen into water. So in summary, the incentive is basically around $1,600 per horsepower saved on motors that run all the time. 50 to 70% of the cost can be covered. No project is too big or too small, and the incentives can work with other funding sources. And there's typically no cost associated with it, and the paperwork is minimal compared to typical infrastructure funding. I briefly wanted to mention strategic energy management. It's basically helping facilities with low and no cost opportunities for savings. Cascade has worked with over 70 sites in the last 3 years, and they've achieved an average of 9% savings with these low and no cost energy opportunities. And I really like this quote from Mick with the city of Ketchum. He said, "The level of treatment wasn't affected, but we reduced our energy consumption for that process by about 15%. And I think that just is great because it speaks to saving energy but not sacrificing water quality. And whether it's a capital project or an O&M or low-cost project, that's really critical and key, is that we're not sacrificing water quality. We're helping the system operate more efficiently and still achieve the water quality." I'm kind of running short on time, I think, but just one example of an O&M type thing is heating. If you've got uncontrolled heating, it can be expensive. This facility just had their heat on, and so in the winter you can see a lot of orange, and that's because they were spending a lot of money on heating versus pumping costs. And so they spent, over a 3-month period over the winter, they spent $17,000 on that facility, but $7 out of $17,000 wasn't even for pumping. It was just for heating. So they were able to save money just by setting a thermostat where, not for human consumption, but just to prevent freezing. So if people aren't going to be in a facility, then there's no need to heat it for human occupancy, and same for air conditioning. So there's big O&M opportunities are typically with reducing operating pressures and flows of plant fluid and air systems, so like compressed air, plant water. If you've got a 100 PSI air system and you reduce it by 2 PSI, you can typically save 1% in energy of that system. Reclaimed water isn't free because you're treating your water through your plant and then you're pumping it around for plant water. So one facility, they reduced their water pressure from 106 to 60, and then also reduced it where they didn't need to use it, and they were actually able to save $6,000 a year just on plant water. Control set points can be big savings. So typically, on average, if you reduce DO by 5 milligrams per liter, you can save 6 to 7% of your aeration energy. 2 milligram per liter is typical, but some systems are able to run lower than that. And we always encourage this as baby steps. Don't just reduce it by a lot. I mean, do incremental small changes and see if it works. And then when you hit a point where it's not working, then stop and go back to where it was working. But if you're running really high, there's probably a lot of potential for savings. Lift stations, if you increase the wet well level, you can save energy. Typically, if you were if you had a ROS pump with 20 feet of head at normal operating point, you raised it by 6 inches, you could save 2.5% energy on that. So how do you get started? Well, you can call or email me and I can help you, or direct you to someone who can help you, or you can call your utility and let them know that you are interested. And now I think if there's time, we can take questions.
All right, thank you, Wendy. It's a great presentation with a lot of useful information. Let's see. Yeah, so if you have any questions for Wendy, you can use your Q&A, I guess that window, chat window, to submit your question. Well, here's the one, Wendy.
Okay.
So the question is, if my plant has replaced the air pumps and the air actuated valves with electric pumps, but not reevaluate our compressed air system, could we save energy?
Yeah, there's potential to save a lot of energy for that. So you're probably producing more air than you need. It depends on the compressor. So I was at a facility recently and they had done just that, and they had an inlet modulating compressor, and so just for going from the type of compressor they had and going to a VFD, getting a new compressor with a VFD, the payback was going to be just a couple years. And then some facilities, depending on if they have air receiver tanks to store the air or if they're just constantly producing air, definitely there's potential for savings with compressed air systems, and even just reducing leaks in systems can save a lot of energy on your compressed air.
All right. All right, and the other question is, if VSDs reduce power savings, when do you recommend them for soft starts of a pump?
Yeah, if you don't need a VFD and we're going to put one on for a soft start, we would not recommend doing that, because it's going to be less efficient. You're going to lose 3% because of the VFD. So we wouldn't recommend using a VFD if what you actually need is a soft start.
All right, cool. Thank you. And the other question is, we don't have a SCADA system. Are there tools that we can use to see how much energy equipment is using?
Yeah, so a lot of systems, even if they do have SCADA, sometimes they don't have, they don't monitor the energy use, don't have any kind of sub-metering. And so the utilities, Idaho Power and the other utilities typically have tools they can loan out. So you could actually borrow it and log data or measure how much you're using. And so you can definitely contact your utility and they can kind of help you figure out what would be a good project and if it's worth it. That's kind of the nice part about working with your power provider, is that you might not know if it's a good project. You might not have any idea how much energy it's using or it could save. And so they can kind of help you with that, figuring out if the payback is worth it for your facility or not.
All right. Great, thank you. I guess due to the time limit, let's move. Oh, okay, we got another one. Hold on. Okay, we have another question. So a utility can contact their power providers or Cascade Energy to have a scoping audit performed. Exactly what is included in scoping audit?
So scoping audit can vary, but it can be if you don't have any project in mind and you just want someone to come and kind of walk through your facility and identify potential things you could do and then come up with some rough calculations. Typically, there's not any data logging. So it's really just kind of looking at your motors and the nameplates and then doing kind of making assumptions to do quick energy calculations and give you just kind of an overview of what might be good projects. So that's what a scoping audit typically is. And Cascade doesn't do it in every area in the Pacific Northwest. It's going to depend on who your utility contracts with, but you can definitely, I can still connect you with the right person if we don't serve your area.
All right, thanks, Wendy. So yeah, we'll move on to the second presentation, but if you have any more questions for Wendy regarding her presentation, we may have some time at the end of the second presentation. All right, so our second speaker is Gail McCoy from Washington State University Energy Program. Gail worked at a Washington State Energy Office and a WSU Energy Program as an energy system engineer for over 30 years. He has conducted many audits of steam, process heating, compressed air pumping, and motor and the drive system at industrial, commercial, and institutional facilities. Currently, Gail is responsible for conducting qualification screenings and offering technical assistance to those interested in installing CHP, so the combined heat and power projects through the Northwest Combined Heat and Power Technical Assistance Partnership, funded through the U.S. Department of Energy. His client groups include industry, universities, military bases, commercial facility, wastewater treatment plants, dairy, and government buildings. So Gail, I guess without further ado, I'll turn it over to you.
Okay, thank you, Meow Meow. One thing in common with Wendy's presentation is the services that we offer through the Department of Energy's Combined Heat and Power Technical Assistance Partnership Program are free. And what we want to do is identify opportunities and then provide advanced technical assistance as needed to kind of move a process down the development pipeline. So what I'm going to cover today, I'm going to give you a brief overview of the Chp Tap program. Then I'm going to talk a little bit about what combined heat and power is and what the benefits of considering this type of project are. We're going to talk about Chp deployments in the United States, as well as at wastewater treatment plants. We're going to talk about biogas conditioning, CHP plant operation at wastewater treatment plants, and then talk about the various steps involved in implementing the development process for a CHP project. Quickly about CHP, we engage with end users, we engage with stakeholders, and the key is we like to think we offer fact-based, non-biased education, information, and technical support. In terms of technical services, we'll do what we call a screening opportunity analysis. We'll look at the potential for CHP at your site. Is it strong, moderate, marginal, or non-existent? We'll help you determine that. We're one of 10 CHP TAP regional centers. We at WSU have responsibility for CHP projects in Washington, Oregon, Idaho, and Alaska. It's very interesting when we get together with our contemporaries from the other region because a CHP is a common thread, but everybody has their own concerns or considerations. Texas and the Southeast and the Mid-Atlantic are really concerned with resiliency and reliability during hurricanes. Pennsylvania and New York are really exploring microgrids. If you go down to Texas and Louisiana, they're looking at CHP at oil and gas facilities. The Midwest, maybe at ethanol production plants. California has some very favorable feed-in tariffs for biogas from dairy operations or wastewater plants. And the Northwest, kind of what distinguishes us besides our low electrical rates, is we have more biomass-based CHP than some of the other regions. So an overview of CHP, what is it? It's simply sequential production of electricity and heat by a single power plant. So it could be a gas turbine with the hot exhaust gases being routed through a heat recovery steam generator to produce steam at a desired pressure. The advantage of doing that is that it's more efficient than separately producing electricity at a power plant, which might have an efficiency, including transmission and distribution losses, of 32 to 44%. An on-site boiler might be 80 to 84% efficient in terms of producing heat, but the total efficiency, if you purchase separately, is around 50%. Your CHP project can be up to 75 to 80% efficient. And of great interest now is greenhouse gas emissions. You have the potential, based upon your generating mix, to reduce gas emissions by 30 to even as much as 55%. So how does a CHP project work? You take a fuel type, and it can be gaseous, solid, renewable, or even waste products. You put it through a prime mover, which can be a reciprocating engine, combustion turbine or gas turbine, a microturbine, steam turbine or fuel cell. The prime mover turns a generator to produce electricity, either for on-site consumption or to sell to the utility. The exhaust gases or waste heat from the prime mover go into a heat exchanger to produce useful and usable thermal energy in the form of steam, hot water used for either space or process heating. Also, process cooling is a potential if you want to consider absorption chillers. So what are the benefits of CHP? It's more efficient, and that translates into lower operating costs, but does require, of course, an upfront or capital investment. It results in reduced emissions, not only of greenhouse gases, but also of priority pollutants. You can increase energy reliability and what we call resiliency. And lastly, on-site generation can reduce grid congestion and also avoid transmission and distribution losses, which might be as much as 3 to 7% of the energy used on site. With our different prime movers, and the different prime movers generally come in different cost-effective size ranges. Typically at wastewater treatment plants, you're going to see the use of lean or rich burn reciprocating engines, perhaps microturbines, although I'll talk to you later about gas treatment requirements. Down in California, they've had some fuel cell applications, but I want to point out these are generally what they call virtual applications, where the biogas would be treated or conditioned at the treatment plant, injected into a pipeline, and then a CHP project miles away at a site in need of thermal energy would pull out pipeline gas, treat that gas, and then use it in the CHP project. Fuel cells are very unforgiving regarding contaminants in the biogas fed to them, and we have had examples of sites at treatment plants where fuel cell stacks have had very short lives. Now, also of great interest right now, or sites greatly interested in CHP, include hospitals, healthcare centers, nursing homes, and the driver for these end users is really resilience. You've all heard about Puerto Rico, the East Coast, where nursing homes lose power for a long duration outage. Their backup emergency generators might fail, and having a heavy-duty CHP project on site can literally be a lifesaver. Other critical infrastructure sites include police, fire, and public safety related sites, centers of refuge. If you're going to send people to a conference center or school, it would be nice if that had the generation to be able to provide heating, hot water, and food services for the ones who are seeking shelter. Military, they consider themselves as mission-critical facilities, and obviously they want reliability, redundancy in terms of types of fuel that can be combusted, as well as multiple sources of steam or electricity generation. So CHP can improve critical infrastructure resiliency, and it can be designed to continue to operate and provide an uninterruptible supply of electricity and or heating and cooling. So what about CHP deployments in the US? The first thing is CHP is not a new technology. It's actually a very old technology. Before there was a grid, CHP was the only way to get electricity and thermal energy available at industrial sites. In the US, there are 4,434 CHP projects in operation with a combined 81,300 megawatts of generating capacity. Most of the generating capacity is in industry. It's in the chemical industry, petroleum refining, pulp and paper. More recently, we've been looking at smaller projects in commercial and institutional facilities. And part of the reason for that is you have the space heating and water heating loads that are coincident with electrical loads. And commercial facilities tend to also pay higher electrical rates than industrial facilities. Here's a map showing the CHP projects in the US. I haven't counted the dots to verify that there are 4,400 of them, but you'll notice they're clustered in the areas of the country with high electrical rates. Other things we'll see around the country is some areas have adopted time of day rates, and not only the magnitude of the rate, but the shaping of the rate can affect your CHP project design. You know, in other words, do you want to oversize and provide gas storage and produce more energy during times of need? Well, what about CHP and wastewater treatment plants? The drivers are energy cost savings. A lot of times end users are responding to federal, state, and local utility incentives, and a great example of local or state-specific incentives is the Energy Trust of Oregon. A lot of times local governments establish sustainability or greenhouse gas reduction goals, and CHP can help there. CHP can provide public relations and green benefits, which is important to the political folks that are involved with local governments. You can have enhanced reliability, even though the treatment plants have emergency generators. A lot of times you can install the CHP during a regular facility upgrade, and sometimes avoid the need to replace equipment that's at the end of the life by substituting CHP to replace their functions. There are ways of increasing biogas production at a wastewater treatment facility, which can increase CHP energy generation and make it more cost effective. A lot of times with the CHP project, you can have enhanced biosolids management, maybe produce co-products that can be used as distributed or sold as fertilizers. And finally, the utility needs to be aware that the CHP project is there, and they are through their interconnection standards and requirements. And that allows the utility, if they have a load shedding plan in place, to know that if they drop the wastewater treatment plant as a customer, that they have good, reliable, and adequate backup. 2 rules of thumb: a typical wastewater treatment plant processes 100 gallons per day of wastewater for each person they serve. And of course, this does vary based on groundwater infiltration. The other rule of thumb is each 1,000,000 gallons per day of throughput is enough flow to produce enough biogas in an anaerobic digester to produce 30 kilowatts of electrical generating capacity. So if you have a 10 MGD treatment plant, do the math and you say, gee, it looks like a 300 kilowatt project might be appropriate at my site. Well, here's some biogas production numbers from a treatment plant in Idaho. They monitor their biogas, which is not always the case. They know how much is used in boilers for digester heating. You can see that use go up in the winter. The remainder goes to a flare. But the total over the course of the year is fairly constant. It's fairly stable. And that's a very nice trait when you're feeding it into and sizing, say, a reciprocating engine. The BTU content of biogas, it varies, depending on the waste you're dealing with, but a lot of times it's between 450 and 620 BTUs per standard cubic foot of biogas. This particular plant is producing 43.38 million standard cubic feet of biogas per year. And, okay. Well, the best candidates for CHP at wastewater treatment plants is those with a consistent source of organic matter, with a high and constant thermal load. Now notice the digester load in the previous slide went down in the summer. And so that plant would be nicely served if it had, say, an adjacent facility that had thermal loads that could be met with excess waste heat from the CHP operation. A CHP is more cost effective when you have higher electrical energy costs. Kind of a rough cut point is 6 cents a kilowatt hour, obviously 10 cents a kilowatt hour. Not good for the end user, but better from the standpoint of CHP cost effectiveness. I mentioned reliability concerns. Everybody has concern over future electricity prices. I've never talked to any end user that said, yeah, we really don't have any concern over what's going to happen in the future. Interest in reducing environmental impacts and greenhouse gases. And a lot of times CHP can be interwoven into a plant expansion or new construction. Now, how many CHP projects are in operation at wastewater plants in the U.S.? Well, you have some CHP projects among the 222 that have very high capacity because they're using biogas as well as purchasing natural gas. And co-firing is always an option. We have 158 systems nationwide that have prime movers that are only fed with biogas. And those plants produce in the aggregate 323.7 megawatts. What about the existing potential in the Northwest? This is plants that are fairly sizable, that have anaerobic digesters already. Here's the number of sites by state, 37 in the state of Washington. Total number of candidates for CHP is 63, with a total of 9,000 kilowatts of potential generation, which is a little over 9 megawatts. In the total US, we have about 1,303, end-use wastewater plants with CHP potential. Now, I mentioned biogas conditioning. What are we talking about here? Generally, we're talking about moisture, hydrogen sulfide, and siloxanes. Hydrogen sulfides are found in biogas produced from all wastewater treatment plant digesters. The concentration of hydrogen sulfide can vary tremendously. It can go from 200 to over 3,500 parts per million by volume. H2S oxidizes into sulfur dioxide in the combustion process, forming sulfuric acid, which dissolves into water droplets that can condense out in your system. This can damage the prime mover, the exhaust systems, heat recovery devices, and stack liners. So hydrogen sulfide definitely has to be removed to prevent damage to your prime mover and affiliated equipment. Well, siloxanes are a family of organic silicon compounds that come from additives to personal care products such as shampoos and soaps. They tend to pass through the wastewater treatment plant process, accumulate in sludge, and volatilize to form a contaminant in biogas. When combusted, the siloxanes form a glass-like deposit that is harmful to reciprocating engines, gas turbines, microturbines, and fuel cells. And the different prime movers, manufacturers, have established allowable siloxane limits for their equipment protection. Now, I'll give you an example. The concentration of siloxanes also varies in biogas. It can vary from 2,000 up to 15,000 parts per billion. Hydrogen sulfide 200 to 3,500. Microturbines, for example, capstone microturbines have established a siloxane limit of about 5 parts per billion by volume. So biogas treatment systems have to be custom designed based upon the biogas concentration of these harmful components and the allowable concentration limit or tolerance of the particular type of prime mover. Now here's what siloxane deposits look like. The left picture shows a recuperator from a microturbine. A microturbine recuperator is used to preheat combustion air and improve electrical generating efficiency. Generally, they would pull the exhaust gas temperature down from 800 to 1,000 degrees Fahrenheit to about 550. Well, you can see this recuperator with this glass-like deposit on it is not going to transfer very much heat. Select siloxane deposits result in a decrease in project efficiency, an increase in heat rate, a reduction in power output, formation of hot spots, increased maintenance cost, and premature equipment failure. A treatment train or process looks kind of like this. You extract the digester gas, it goes through a hydrogen sulfide scrubber. Then you remove moisture with a chiller. You generally would then go through a gas compressor through a siloxane scrubber system or activated carbon treatment tanks. And the compressor, by the way, would be sized to provide the engine generator with the biogas, the clean biogas, at the pressure needed for injection into the combustor. That would be about 75 psig for a microturbine, maybe 3 psig for an engine genset. So you're removing hydrogen sulfide, moisture, siloxanes, and any particulates. Here's a picture of a gas conditioning system. This is installed at a 250 kilowatt biogas fueled wastewater treatment plant project in Washington State. And this is a pretty comprehensive system. These large chambers are for the siloxane treatment. Generally, you would want to plumb them in series, not in parallel, to avoid a siloxane breakthrough. And you can imagine this system cost a bit of money. You might find your biogas conditioning system costing as much as 40% of your total combined heat and power project. There's also a considerable economy of scale. What we're doing here is looking at biogas flow rates, the million gallons per day of treatment plant capacity that would produce that biogas flow rate, potential installed generating capacity, and then the gas treatment system equipment cost in dollars per kilowatt of installed generating capacity. So a real small project might be paying $2,500 to $4,000 per kilowatt installed. A very large project, you can see that drops to about $200 to perhaps $400. So for both the generating equipment itself and for the gas treatment, there's very strong economies of scale, favoring the larger wastewater treatment plants. So the conclusions from biogas conditioning, there's a considerable economy of scale. but it's also essential to ensure that the biogas is of acceptable quality for use in your prime mover. Conditioning systems are custom engineered with the removal efficiency based upon the inlet gas concentrations and equipment tolerances. Without proper gas conditioning, maintenance costs will increase dramatically, system efficiency will deteriorate, and you'll have increased downtime. When you're doing a cost effectiveness analysis, you not only include the upfront cost of biogas conditioning, but also the maintenance cost of operating the gas compressor and changing out your filter media. Let's talk a bit about CHP plant operation at wastewater plants. In a typical industry, we might talk about electrical load following or thermal load following. In wastewater treatment plants, we talk about gas load following, biogas following. Basically, the electrical engine output is established by economically maximizing the combustion of biogas. So if your biogas production goes down, or the biogas production goes down, your engine load will also, or engine output will also go down unless you have the ability to supplementally fire either on-site stored propane or have access to on-site natural gas. Engine output changes as the biogas production varies, so sometimes you might want to consider biogas storage. I talked with one person at another Chp Tap. Their utility had very strong time of day rates. The rate might be as much as 3 times more for energy purchase during peak period hours than during nighttime hours. So they were considering installing gas storage and then tripling the size of their prime mover to produce all of their energy during the period when it's when it's valued the highest. CHP typically doesn't meet all of the electric load at a wastewater treatment plant using anaerobic sludge biogas alone due to limited biogas production, but that can change if you co-digest food processing plant wastes or if the wastewater treatment plant accepts fats, oils, and grease or fog fuel. And we'll talk a little bit more about that later. You'll also find the wastewater treatment plant might produce excess thermal energy if it's only used for digester heating. And there have been instances where wastewater plants have used excess thermal energy for heating of greenhouses, or sometimes excess biogas might be compressed and shipped to a adjacent boiler or thermal host. Let's talk about fog or fats, oils, and grease potential. Generally, this material is collected from food service establishments and disposed of in landfills. So there's an industry out there of fog haulers, just like there are of septic pumpers. Tests conducted by Clean Water Services, who operate the Durham Advanced Wastewater Treatment Facility in Oregon, show that fog produces more than twice the amount of biogas as food waste. And what they're showing here is the cubic meters of biogas produced per ton of product. So fats, oils, and grease, you're over 900. Food scraps, you're a little bit over 200. Bakery waste, a little bit higher. Brewery waste, lower. Chicken manure, far below fog in terms of its biogas production potential. It's estimated that each gallon of grease produces about 13 standard cubic feet of biogas. Now here's a fog receiving station at the Gresham Wastewater Treatment Plant down in Oregon. Note that these stations can accept or generate tipping fee revenues. So basically, the haulers are paying you, you being the wastewater treatment plant operator, to deliver free fuel to you. That can be quite exciting. Fog loads are variable in solids contents, and haulers don't work on weekdays or weekends. So you want to put in fog storage tanks to basically have an inventory and to kind of mix the fogs to produce kind of a standard fog quality. And these are two 70,000 gallon tanks, I believe, at the Durham wastewater treatment plant. Co-digestion of fog with sewerage sludge can basically double your biogas production. And what we're talking here is a wastewater plant in these size ranges may be accepting 12,000 to 15,000 gallons of fog per day. The availability of fog results in the installation of increased electrical generation and the capture of economies of scale in biogas treatment and in your CHP project itself. Now, this is kind of an interesting chart for the Gresham wastewater treatment plant. They've achieved energy net zero through a combination of CHP, renewables, and efficiency. The red shows the electrical energy consumption at the site. In 2005, this plant installed a 395 kilowatt CHP project. That met almost half of their electric load at that time. The yellow is the output from a 420 kilowatt ground-mounted photovoltaics project. Here you can see the red going down, and that's because of an efficiency program that they undertook that resulted in the installation of turbo blowers and I think variable speed pumping on their RAS pumps. The blue then is what happened after they started collecting fog and putting the additional biogas, plus additional biogas that resulted from plant expansions through a second 395 kilowatt CHP project. You can see where the on-site generation got to the point where it was exceeding the power requirements of the site. In 2010, the city and the managers of the plant decided to shoot for or establish net zero as a goal, and they achieved that goal by 2015. A few project snapshots. This is a 150 kilowatt project at a site, a wastewater treatment plant in Danville, Illinois. What I wanted to show you here is how the smaller equipment comes packaged in soundproof enclosures. Basically, DOE, Department of Energy, is talking a lot about plug and play for small CHP projects. And basically, some of these projects come in shipping containers, and you basically do the electrical hookup, electrical interconnection, hook up to your thermal loads, and the project is pretty much good to go. Here's another plant, a bigger plant, 11 million gallons per day. They've got a 280 kilowatt reciprocating engine. Here's the cost. I would look at that and say, boy, that's a pretty high cost. A lot of times you'll find that CHP projects are integrated into other plant enhancements, and it's fairly hard to break out the CHP project cost itself. Here's a plant in Des Moines, Iowa. They're treating 72 million gallons per day. They've got about 4.6 megawatts of capacity. They've got 5 engines, and 5 engines, just like in the efficiency talk, multiple units enable the plant operators to follow biogas loads in an efficient manner. And also 1 engine at a time can be brought down for maintenance so that the other 4 engines are still available to generate and meet plant loads and offset utility imposed capacity charges. Well, how can the CHP TAP help you get a plant scanned and help you down the development path if it's cost effective? First, give us a call. We'll ask you a series of screening questions, and we have software tools so we can take general information and do what we call a screening technical assistance analysis. We also perform third-party reviews of feasibility assessments. We used to do feasibility studies, but no longer. We do what we call advanced technical assistance, and that can look at emissions aspects of a project design. We can look at economics. We can look at greenhouse gas reductions. As I was saying, emissions after treatment requirements. We can also perform third-party reviews of engineering analyses done by others, and we can review specs and bids, and basically give kind of an unbiased opinion to the plant developer. Here's a sample of the types of screening questions we asked. Are you concerned about reliability? Do you operate for more than 3,000 hours a year? Of course, wastewater treatment plants always exceed that. Do you have thermal loads throughout the year? If so, describe them to us. And this helps us to do a qualitative assessment of whether or not the factors needed for a CHP project to be successful are indeed present. Then we ask if you have an existing central plant. Do you expect a facility upgrade in the near future? Have you already installed energy efficiency measures? Are you interested in reducing your impact on the environment? Do you have access to additional biomass resources? All of these are factors that go into a plant design. Early questions for wastewater plants. Can you provide 1 year's worth of electrical and thermal energy consumption? And have you measured and can you provide biogas flows if indeed your plant already has an anaerobic digester? And lastly, we ask if you've done an analysis or assay of your biogas. We want to know what your energy content is, as well as the concentration of contaminants. And of course, we ask what the maximum and average flows in are to your facility. Ideally, we like to look at that by month. So are you producing biogas? How much? Does the amount change seasonally? How is it currently being used? Is it for flaring? Are you burning it in boilers or a part of it for digester heating? what additional revenue streams might result from a biogas CHP system? This is just an example of the output from one of the CAN software tools that we use. We basically look at the baseline or base system case, the case with CHP. We look at the difference in total operating cost, and then we're able to determine simple payback on investment for the CHP project after taking maintenance costs for both the prime movers and the biogas conditioning into account. Advanced technical assistance, again, that can deal with emissions, electrical load profiling, thermal profiling, installation cost estimates. We can talk about the trade-offs between using one type of equipment versus another. Prime mover selection depends on whether you have a need at your site for steam versus hot water. And of course, a lot of times we get involved with financial calculations. One example might be estimating levelized generating cost from, say, a back pressure turbine project at an industrial site. We'll help you review existing CHP proposals if you get to that stage of development. Technical challenges, biogas cleanup equipment, space constraints, staff education, training, and engine certification for the prime mover that's selected. CHP operators, wastewater plants can elect to contract out for maintenance, have in-house staff do it, or maybe contract out for a few years to allow their staff to become totally familiar with the equipment and maintenance requirements. Definitely contact a utility early on to find out what their interconnection requirements and standards are. Look at maybe power sales of excess electricity to the utility. Look at whether or not they offer net metering, and look at the value of renewable energy credits. They could be transferred to the utility, and of course the prices for renewable energy credits is constantly changing. Permitting issues, definitely talk to your local air quality control folks early on. Generally, we found that small projects don't need after treatment. You're not going to be a major source and emit over 50 or 100 tons per year of a priority pollutant. But again, contact them as soon as you know what your prime mover emission rates are. And notice that some engine manufacturers offer standard and low emitting types of equipment from a NOx standpoint. Look at the possibility of increasing your biogas supply due to fog or food processing plant waste. And then don't forget project financing. So summary, CHPs are proven technology and proven at wastewater plants, which offer a source of free, if not fuel, at least energy. I don't consider it fuel until it's been conditioned, while running continuously. Utility renewables mandates, and in some states feed-in tariffs, are creating a market for RECs and renewable energy projects. There are opportunities in the region to learn more by visiting wastewater plants that have already installed combined heat and power. And finally, engage with the Northwest CHP TAP. Pick our brains. Let's talk about your project. We offer free screening, technical assistance, and let you know what your simple payback might be, we roughly calculate the appropriate equipment size and then indicate if you have strong marginal, moderate potential for a CHP project. Basically get started by contacting the Northwest CHP Tap. Here's our contact information. And with that, I'm open for questions.
Thank you, Gail. Yeah, we got a question here. What is the average cost, like $1 per kilowatt hour from a cogen when gas treatment and engine maintenance costs are included?
Boy, I love questions like that because the answer is easy. It depends. And that's what the screening technical assistance study is all about. We can determine your cost of production, and to create benefits on site, the cost of production always has to be less than the cost of utility provided power. Now, I'll give you a great example. We looked at a digester that would be operating on food processing plant wastes in the Tri-Cities area of Washington State. The utility rate was less than or about 4 cents per kilowatt hour. And even with free fuel and no siloxanes available in the food processing plant wastes, we came up with a simple payback of about 6 years. So the project was good, but from an industrial standpoint, they like to see a 2 or 3 year simple payback. So we're waiting on that project until the time is right, or until the value of renewable energy credits goes up. But bottom line, the costs vary of production, as well as the utility rates vary, even based on rate schedule within an individual utility. So our offer to you is, let's do some calculations and find out if you have a cost-effective project.
Thank you. And the next question is electrical production with microturbines and reciprocating engines similar?
Pretty similar. The microturbine would have a little bit lower electrical generating efficiency, maybe 28% versus 32 to 34% efficiency. So you have to get into, which is better. You have to look at the cost of gas conditioning. You have to get a quote from the distributors for the two types of units. Typically, microturbines tend to come in discrete unit sizes like 65 kilowatts or 200 kilowatts, but they can be combined. So a lot of times you see a shipping container and you can include 200 kilowatt units in it up to 1,000 kilowatts of output. So if you have multiple units, you don't tend to see of the same capacity, you don't tend to really see an economy of scale from going to 2 units for 6 or more. But those two generating technologies are competitors. You have to look at the emissions, and the microturbine is very low from the standpoint of NOx emissions. Does that have value in a particular site? Does that avoid the after treatment that a recip might have? If it's a large recip, there are just a host of questions that are best answered by doing a good screening analysis and cost effectiveness study.
All right, thank you, Gail. Yeah, looks like we're about the time. if there's no more questions, we will end the webinar. Thank you all for participating. Hopefully this webinar provides you some ideas on the energy saving and recovery opportunity at your treatment plants or facilities. Also thank you, Wendy and Gail, of course also Mike Rainey, for your time and the great presentation.
Well, thank you.
Thank you everyone for attending this PNCWA webinar. This is Mike in the PNCWA office. Remember, you will get the PDFs of the presentations here within the day, and you will get an email in 24 hours with a link to the form to request CEUs. We have a recording of the webinar, and as soon as that is processed, we'll have it online also. Thank you very much. Thank you to the Sustainability Committee and the panelists. Great job, everyone. Thank you. I'm going to leave the window open for questions for a few minutes as people are leaving the webinar. If you have a question that you would like to ask that you didn't submit yet, the panelists can still answer it by email. Okay, everyone, this is Mike in the PNCWA office again, and I think we're going to close this out and watch for that email with the PDFs and the request for CEUs, and thank you all.